Hello everybody, welcome to the experiment 9 which is called Biot-Savart experiment. This experiment consists of two parts. In the first part, Biot-Savart law will be experimentally examined by measuring the magnetic field of a circular conducting wire that is applied current. On the second part, magnitude of magnetic field occurring in a coil will be analyzed. Biot-Savart law expresses that direction and magnitude of magnetic field depends on the length of the conductive wire that current passes on it, direction and magnitude of the applied current. Graphical representation of the law can be shown here, and formulation shows us what magnetic field depends on. First part of the experiment is examining the magnetic field through a conducting circular wire, and equipment for this part is Tesla meter, DC power supply, conducting wire with 3 different windings, and holder for the conducting wire, and this is the probe of the Tesla meter, and some jumper cables. So let's carry out the first part of the experiment. First part of the experiment is measuring the magnetic field through a conducting wire. Here I set the current to 5 amperes, and the probe of the Tesla meter is at the center of the magnetic wire, conducting wire, and the magnetic field value is 0.12. Now I will change the distance to 1 centimeters. When it is 1 centimeters, the magnetic field value is 0.10. When it is 1.5 centimeters, it is 0.08. When it is 2 centimeters, it is 0.07. When it is 2.5 centimeters, it is 0.05. When it is 3 centimeters, it is 0.04. When it is 3.5 centimeters, it is 0.04. When it is 4 centimeters and it is far away from the center of the wire, the Tesla meter will measure it as 0. Now I will change the wire, and I will use with the number of windings 2. Now I will repeat the experiment with the number of windings 2 wire. When the distance is 0, I mean it is at the center of the wire, the magnetic field value is 0.23. When the distance is 1 centimeter, the magnetic field value is 0.19. When the distance is 1.5 centimeters, it is 0.16. When the distance is 2 centimeters, it is 0.13. When the distance is 2.5 centimeters, it is 0.10. When the distance is 3 centimeters, it is 0.08. When the distance is 3.5 centimeters, it is 0.07. When the distance is 4 centimeters, it is 0.06. When the distance is 4.5 centimeters, it is 0.05. When the distance is 4.5 centimeters, it is again 0.05. When the distance is 5 centimeters, it is 0.04. When the distance is 6 centimeters, it is the Tesla meter measuring the magnetic field as 0, and when the distance increase, it will continue like that. It means it is very small magnetic field. Now I will repeat the experiment with the wire of number of windings 3. Now I will repeat the experiment with the wire number of winding 3, and the probe of Tesla meter is at the center of the wire, and the magnetic field value is 0.34. Now I will change the distance. Now it is 1 centimeter away, and the magnetic field value is 0.31. Now it is 1.5 centimeter away, and the magnetic field value is 0.28. Now it is 2 centimeter away, and the magnetic field value is 0.23. Now it is 2.5 centimeters away, and the magnetic field value is 0.19. Now it is 3 centimeters away, and magnetic field value is 0.15. Now it is 2.5 centimeters away, and the magnetic field value is 0.12. Now it is 4 centimeters away, and the magnetic field value is 0.10. Now it is 4.5 centimeters away, and the magnetic field value is 0.07. Now it is 5 centimeters away, and the magnetic field value is 0.06. Now it is 6 centimeters away, and the magnetic field value is 0.04. Now it is 7 centimeters away, and the magnetic field value is so small that the Tesla meter cannot measure it. Second part of the experiment is magnetic field of a coil. When current is passed through a coil, a magnetic field occurs in the coil. The magnitude of this generated magnetic field depends on the value of the applied current, the length of the coil, and the number of windings. The variability of the magnetic field along the axis of an N-wound coil with a coil length of L is examined, assuming that the coil consists of infinitely small numbers and lengths of coils, and the infinitesimal formulation can be seen here. Further analysis and formulations can be found in the lab manual. The equipment of second part of the experiment is similar to part 1, and they are Tesla meter and and DC power supply and holder. Also, we will use three different lengths and windings of coils, and also we will use some jumper cables. The second part of the experiment is measuring the magnetic field through a conducting coil. For this we will use three different coils, and for this one the characteristics of this coil is it has 100 windings and 42 millimeters of diameter, and I set the probe of the Tesla meter at the very beginning of the coil, and the magnetic field value is 1.19. Now we will set the probe at the right of the middle of the coil, and magnetic field is 2.32 milliteslas. Also the current is 1 amperes. Now the coil is twice longer and also has twice winding number. It has 200 winding numbers, and again it is a diameter of 42 millimeters. At the very beginning of the coil, the magnetic field value is measured as 1.21, and now I am setting the tip at the middle. It is 2.82 milliteslas, and the current is again 1 amperes. Now we will carry out the experiment with a longer coil. It has a 300 winding and 35 millimeters diameter, and it is at the very beginning of the tip of the Tesla meter is very beginning of the coil, and the magnetic field value is 1.12 milliteslas. Now I'm setting the tip at the center, halfway of the coil. And at the half point of the coil, the magnetic field value is 2.81 milliteslas, and the current is again 1 amperes.